Now we talk about the cardinality of sets. That's an extremely important concept to study the category of sets. It's very simple to understand the concept of cardinality. It's essentially the number of elements in a set. So if we have a set X, A, B, C, the cardinality is 3. So usually we denote it using lines. So simple. But many of our future study will be based on the cardinality. To get familiar with that, we have empty set, no element. So cardinality is 0. And of special importance is the singleton. Singleton is any set that contains a unique element. It can be anything. And the cardinality of singleton is always 1. So usually we do not distinguish between the different singleton that has different elements like or A or 1, etc. They are equivalent or they are equal. So usually we denote it using a 1. It could be any of them. And you can also have binary set 1, 2, 2 elements. Or we can use true, false, or 0, 1 in Boolean algebra. Okay, so the minimum one is 0, and then 1 and 2 equals empty set singleton, binary set, and go on. N. If we have a natural number n equals to the cardinality of a set, the set X is a finite set. So as we have discussed it previously, that a set is an object of the category of set. So we can write like this. So for finite set, we also have a category, the category of finite sets. So if X is a finite set, we can say X is an object of fin set. Fin set is a category of finite sets. And the arrows is the function from one finite set to the other. So the category of finite sets is a subcategory subcategory of the category of sets. And we can say that a finite set as a category has correspondence with the natural number plus 0. And for those infinite set, like the set of integer, this is not for, it's an infinite set, and it still have a cardinality. The cardinality can be denoted using the Aleph 0. If you have experience in learning real analysis at the beginning of the textbook of real analysis, you usually can see different kinds of infinity. This is infinity. And the number of integers is the minimum infinity, because the set of integers is countable. That means you can enumerate every element of integers just one by one. And according to the results of real analysis, every countable infinite set has same cardinality. So that cardinality is Aleph 0. So right here, and we also have uncountable infinite set, like the set of real numbers or an interval of the real number 0, 1. The cardinality of it is much bigger than the cardinality of integers. So we have Aleph 1 and Aleph 2, 3, 4. So they are infinite. Okay, so given any two sets x and y as the objects of the category of sets, if we can make a map F, if F is a bijection means it's an injection and a surjection. In other words, let me make a explanation for the injection. That means if you have elements x in the set X, and every element in the X can be mapped inside Y. This is injection. Injection means that you can see it's obviously that only when the cardinality of X is less or equal than the cardinality of Y, we can make injection to Y. And this map distinguishes different elements of x1, x2, fx1, x2. So if x1 not equal to x2, using the injection, this distinction can be reflected in the image of those two elements. This is the injection. And for surjection means that if we have x, y, and every element of y can be a destination of the map of f. That means for any y, we can find an x here. It exists x here, and y is the image of f of that element. So surjection, the condition of surjection is like here. So this one is injection, and this one is surjection. You can prove that as a homework. It's not too hard to prove that. So injection less equal than, surjection greater equal than. So if we have bijection satisfying injection and surjection simultaneously, that means we must have x, y. They have the same cardinality. Good. If we have same cardinality, we have bijection. And bijection is essentially the isomorphism between the two sets. So if we have xy with the same cardinality, we can say x is isomorphic to y. So like, for example, AB 1, 2, true, false, plus, minus, north, south, they are all binary sets. They're different sets, and we can easily establish bijection between each pair of them, and so they are isomorphic to each other. So essentially, they are the same. So we have a takeaway. If we take x1, y isomorphic, or even in some sense, in the point of view of category theory, we think they are the same. Observed from the outside, they are the same. Then we have the same cardinality. Okay, so is there any relationship between the cardinality of sets and the linear algebra? The answer is yes. But we should get very familiar with the operation of cardinality.